I can zoom it in. Okay, so that is your, what is that? That is the determinant of A minus lambda I. Are you sure about that? Thank you, 3. That is 1 minus lambda, so that is minus 2 lambda. And then negative lambda plus negative lambda, that is plus lambda squared. Oh, okay, so you didn't arrange that. So you should arrange that to write that as an equation. In this case, the degree is 2, so it should be in quadratic equation. Okay, now we already have the characteristic polynomial, and we can equate this to 0, and that is our characteristic equation. So now we have the equation lambda squared minus 2x minus 3. Then you can solve for lambda. The same way you solve for an quadratic equation for the factors. Can you solve for lambda there? Can I delete this one? Okay. So solve for lambda. So you have lambda squared minus 2 lambda minus 3 equals 0. You can do like this. The same as, this is just similar to x squared minus 2x minus 3 equals 0. If it's not factorable, then you use quadratic formula. But I'm sure this is factorable. So you can do like that, lambda. So you look for numbers. This is what you're going to do. You look for factors of 3 that when you multiply them, it would equal to negative 3. And when you add them, it would equal to negative 2. So what are the factors of 3? Okay, your last term here is 3. So you look for factors of 3 that when you multiply them, it would equal to negative 3. And when you add them, equal to negative 2. So what are the factors of 3? 1 and 3, right? So 1 and 3. But it's negative 3. It could either be negative 1 or positive 3, or 1 or negative 3. But the middle coefficient is negative 2. So that means the larger number should be negative. So it should be x plus 1, lambda plus 1, lambda minus 3. Yeah? You can always check it using the FOIL. See? 1 times negative 3 is negative 3. Then 1 times lambda, negative 3 times lambda, so negative 2 lambda. See? So that's how to factor that. Okay, and then you equate each of the factors to 0. Okay, then solve for your eigenvalues. So you have 2 values here. Yeah. So we have 2 values for, we have 2 eigenvalues. And now we can find the eigenvectors. Alright, going back to the equation I showed you earlier, this one, with the eigenvector equals the 0 vector. Yeah, and this one, a times x equals lambda times x. To do, we calculate the eigenvector for each of the lambda, or each of the eigenvalues. Can I delete this one, the first? Okay, so let's start with lambda, for lambda equals 3. That was 3, right? The other one is -1. So we multiply, we substitute lambda to a minus lambda I. So a minus lambda I is just equal to a minus 3I. And then what is our original matrix? I forgot. What was that? 1, 1. Okay, minus 3 times the identity matrix 1, 0, 0, 1. Okay. Let's. Okay, and then simplify that one. Alright. Okay, so notice that we have -2, 1, 4, -2. We have to make this 0, this one's, the elements below -2 and 1. So in this case, you can apply the Gauss-Jordan elimination. Oh no, reduced echelon form, row echelon form, or just do the elementary operation. So let's say we reduce this one. This should be 0. So what are we going to do? So this would so 4 would be 0. Maybe we can do R2 plus 2 times R1. So what will be the result for that? R2 minus R1. We just skip this one, okay. R2 minus R1 is 4. R2 plus 2 times R1, 4. Okay, that's 0. And then -2 plus 1, that's also 0. Okay, so that is our a minus lambda I for lambda equals 3. But our equation is that one, a minus lambda I times the vector eigenvector equals the 0 vector, because we are interested to in finding the eigenvector. So we can multiply that -2, 1, 0, 0 by this is a minus lambda I. This is from here, right? This one, and this one is x eigenvector from here, the equation. And then this is the 0 vector, this one. Okay, can I delete this one? Okay, so we have -2, 1, 0, 0, x1, x2 equals 0, 0. And now we can equate this, or we can solve this. We multiply -2, 1, and x1. So we have -2 x1 plus x2 equals 0. Is that right? Okay. Alright, so we can solve for the value of x2 here. So we can set x sub 1 equals 1. Then this would become -2 times 1 plus x sub 2 equals 0. So x sub 2 equals 2. Actually, you can use any multiple. Any multiples. You can use like set x sub 1 equals 2. Yes. Apply multiplication. That's 0. That is 0. 0 times x is 0. We don't include the 0. Recall the matrix multiplication. 0. No, because the result of that is not a vector. Yeah, we want to get what's this? The values of x1 and x sub 2 that is contained in vector x. All right, now it's clear. Let's go back to that one. Okay, let's go back to lambda. Where are we? Lambda equals 3. So we got 2x, negative 2x1, x2 equals 0. Okay, to solve for the values, we can set x sub 1 equals 1. So that is negative 2 times 1 plus x sub 2 equals 0. So x sub 2 is equal to 2. Now we have the value of x sub 2 and x sub 1 equals 1. Okay, therefore, the vector, eigenvector, can have the components 1, 2. If x sub 1 is equal to 1 and x sub 2 is equal to 2. But you can use other multiples. Alright, you can use, let's set x equals 2. Then you can solve for the value of x sub 2. You got it? So that means for eigenvalue equals 3, this is the corresponding eigenvector. You can just set any values you want. Yeah. Then x sub 2 is equal to 10. Yeah. But then 5 and 10 are multiples. Both divisible by 5. So you can, your x vector there, you can factor out 5, then you have 2. It's the same. You just multiply by a scalar, which is equal to 5. There, you got it? As long as it's the same, the vector is the same. Okay, so why... Huh? What do you mean? Mm-hmm. Mm-hmm. Oh, what's your question? All right. Okay, 1, 2 there are the elements of vector x, which is the eigenvector. So no matter what number you multiply any scalar, as long as it's 1, 2, then that is this eigenvector for the specific lambda or specific eigenvalue. So in this case, for lambda 3 equals 3, the eigenvector is equal to 1, 2. But you can, or no matter what scalar or number you multiply to it, make sure that you would get the same value, elements for your vector. You got it? You want to try the other eigenvalue, because we have 2 eigenvalues here. How about lambda equals negative 1? You get the eigenvector for that. Yes. Then there's another one here. Okay, we can do maybe we try, let's try, what's this, 3 by 3 after this one. Yes. Yeah, I mentioned you could be any multiple. Any, yes. Any, like say for example 2, 3, like what you picked 5, you will get the same answer. It's just it is multiplied by a scalar. One, 3. You got 1, 3? How did you get 1, 3? So you have, where did you get that? I don't understand. I think you directly did it. You forgot to get your a minus lambda I. This one, a minus lambda I. You do that first. I wonder how you got that. Oh, this one is also, yeah, this one is, oh, you're using the first equation. It will be different. Yeah, because lambda is different. The lambda for the first is 3. So 3 here. But this one is -1. It should be a minus -1 I. So that's what you're going to work on. Yeah, that one. Let me. So a minus lambda I, and your lambda here is -1. So you use that, you plug in that here, a minus -1 I. So this is a plus I, right? Then whatever you get from there, if the bottom is not 0, you use the elementary operation. Okay. And you have 1, 4, 1, 4. Okay, you make 4 and 2 0, so you can we're gonna do here, how do you make a set? Yeah, okay. Oh, okay, you already have here. So you have, oh, you forgot your vector. Maybe what? Okay, this one is correct, and then you'll do like this. You multiply that 2, 1, 0, 0 times your vector with vector components x sub 1, x sub 2 equals 0, 0, and you perform matrix multiplication there. So that is 2 times x sub 1 right? Where are you writing? Okay, 2x sub 1 plus x sub 2. So x sub 2 is equal to negative 2. Okay, that's correct. And then x sub 1 is equal to 1. So you write your vector. Your eigenvector is 1, negative 2. Yeah. You can always check that from here. Ax, what's the other one? Lambda, like that, if they are equal. Yeah, you can always check that. So you put the original matrix 1 1 4 1, and then the vector eigenvector for a specific lambda, say for example lambda 3, the vector 1 2, then lambda here 3, then 1 2, and you check if they are equivalent. Yeah, they're equivalent because they're the same. Okay, you want to try the 3 by 3? It seems like we're struggling here. I'll give you this one, this matrix. Try to solve this. A 1 0 0 3 negative 2 0 2 3 4. Okay, find the eigenvalues and eigenvectors of that. All right, let's move on to linear transformations, vector space. Okay.